So I guess I'll get started. So our next exam and the next set of homeworks and worksheets are all due on November 6th. So that'll be on chapters 2 through 5. We're on chapter 5 right now, so we're still ahead of schedule. And so the exam on that will be on the 6th. So that'll be in a little while. It's a week after next, I think. Yeah. So, continuing on with chapter 5 about earthquakes. Okay. So let's talk about how we measure the severity of earthquakes. There's two scales that are used to measure earthquakes. They measure different things. They are the Richter scale and the modified Mercalli scale. The Richter scale measures how much energy is released during a quake by calculating the seismic wave energy at a standard distance based on the height of the traces you see in a seismograph. So the Richter scale was originally based off the height of the highest peak in the seismograph. It's been modified a bit since then to deal with bigger earthquakes where it doesn't work as well, because it turns out instead of getting higher peaks, you get more of them. And then the modified Mercalli scale. So the Richter scale is about how much energy is being released by this earthquake. The modified Mercalli scale describes the results of the earthquake in terms of felt and observed effects. So the Richter scale is about how much energy did this earthquake have? The modified Mercalli scale is about what did this earthquake do? And the environment can affect a lot about the severity of the effects of an earthquake. So the intensity is a measure of the degree of earthquake shaking at a given locale. It's most often measured by the modified Mercalli intensity scale. But yeah, it doesn't. So for example, modified Mercalli 1, it's not felt except for a few under especially favorable circumstances. 2, it's felt only by a few persons at rest, especially on upper floors of buildings. 3, it's felt noticeably indoors, especially on upper floors of buildings, but many people do not recognize it as an earthquake. 4, during the day, it's felt indoors by many, outdoors by few. It's the sensation like a heavy truck striking the building. 5, it's felt by nearly everyone. Many are awakened. There's disturbances of trees, poles, and other tall objects are sometimes noticed. 6, it's felt by all. Many are frightened and run outdoors. Some heavy furniture gets moved. A few instances of fallen plaster or damaged chimneys. The damage is slight. 7, everybody runs outdoors. The damage is negligible in buildings of good design and construction. Slight to moderate, well-built ordinary structures, and considerable in poorly built or badly designed structures. 8, damage is slight in specifically designed structures, considerable with partial collapse in ordinary buildings, great in poorly built structures, falling chimneys, factory stacks, columns, monuments, walls. 9, damage is considerable in special designed structures. Buildings are shifted off foundations, ground cracked conspicuously. 10, most basically in frame structures are destroyed. Some well-built wooden structures are destroyed, ground is badly cracked. 11, few if any masonry structures remain standing, bridges are destroyed, broad fissures in the ground. And 12 is total damage. Waves are seen on ground surfaces, objects are thrown upwards into the air. Now, magnitude of earthquake is a measure of how much energy the earthquake releases. And it's based on the amplitude of the largest seismic wave a tenfold increase in amplitude of the wave, it results in an increase of 1 on the scale. So every step up on the Richter scale, you're increasing the size of the largest wave by a factor of 10. So it's a logarithmic scale. And each unit of Richter magnitude equates to roughly a 32-fold energy increase. What it is that 2 steps corresponds to just remind myself. Yeah, it's a little bit less than 32. The square root of 1,000. 2 steps on the Richter scale corresponds to 1,000-fold energy. And it doesn't work very well for very large earthquakes, because it turns out for very large earthquakes, you kind of start to saturate the size of the movement. Once you get above a certain point, the Earth doesn't actually move that much more. It just does it repeatedly. So there's a modified version of this. So magnitude versus ground motion and energy. If there's a difference in magnitude of 4, the difference in ground motion is 100,000 times. I would say 10,000 times. The difference in energy release is about 1,000,000 times. The difference in 3 is 1,000 times. Difference in energy release is about 32,000 times. 2 is 100 times difference in ground motion, and the difference in energy release is 1,000 times. And 1 is about 10 times the ground motion, and the difference in energy release is about 32 times. So the Richter scale was developed in 1935 by Charles Richter of Caltech. And this is the most common method of earthquake measurement. When people talk about the magnitude of earthquakes, they're talking about the Richter scale. It correlates the largest seismogram peak during a given quake to the amount of energy released by that quake. And it gives the earthquake magnitude, and it's expressed as numbers. Earthquakes we talk about are between 3 and 9. Earthquakes less than 3 happen all the time. It's just they're barely feelable, so we don't talk about them. And earthquakes, there has not been a recorded earthquake greater than 9. I think the record is like 9.2 or something, and 9 is bad. So the Richter scale is logarithmic. Each whole number increment represents a 10-fold increase in amplitude tracings, and it's a 31 to 32-fold increase in energy release. So magnitude 5 releases 31 times the energy of magnitude 4. Magnitude 6 releases 1,000 times the energy of magnitude 4. And a drawback of the Richter scale is that the magnitude of an earthquake gives no indication of the damage it may cause, because it's just a measure of the biggest vibrations we see on the surface. Lots of factors affect the damage caused. Things like focus location, geologic rock types, population density, and construction types. So you can have very different damage from 2 places that are like close to each other with different ground conditions. So relatively moderate quakes in areas with high population and poor construction techniques can cause considerable damage and loss of life, while more severe quakes in sparsely populated areas can cause very little damage. There's nobody there to get, if there's not much there to get damaged, very little gets damaged. So, and the size of it, a more modern system is known as the moment magnitude system, which is sort of an upgrade of the Richter scale. It measures the total energy release. It's derived by the amount of slip on the fault, the area of the fault that ruptured the surface, and the strength of the rock. And this is good for measuring medium to large earthquakes. So it takes up where the Richter scale starts to fail. So here are some frequency of earthquakes with various magnitudes. Less than 2 The average per year is, they're so common, they're unknown. They're very minor, they're generally not felt by humans, but they may be recorded because the seismograph can be quite sensitive. Very minor earthquakes between 2 and 3, there's like 1,003,000 a year. Sorry, 1,300,000 a year, 1.3 million a year. They're felt by humans, but they don't do any property damage. Their energy release is on the order of 1,800 kilograms of TNT. 3 to 4 is a minor earthquake. It's felt by humans. It's very light. Property damage, if any. Some examples: Texas in 2015, there was a 3.6. Maine in 2006, there was a 3.8. New Jersey in 2009, there was a 3.0. There are about 130,000 a year. From 4 to 5, there are about 13,000 a year. These are light earthquakes. You get noticeable shaking of items indoors, some property damage. There's one in Western Minnesota in 1975, it was magnitude 4.6, and in Arkansas in 2011, a magnitude 4.7. 5 to 6, there are about 13,019 a year. This is a moderate earthquake. There's property damage to poorly constructed buildings. Some examples are Mineral, Virginia in 2011, magnitude 5.8. Northern New York in 1994, magnitude 5.8. East of Oklahoma City in Oklahoma, 2011, magnitude 5.6. Strong earthquakes from 6 to 7, that's 134 a year. These can be very destructive in populated areas, can cause loss of life. Kobe, Japan in 1995 was a 6.9. Loma Prieta, California in 1989 was a 6.9. Northridge, California in 1994 was a 6.7. From 7 to 8, we're talking major earthquakes with damage in the billions of dollars and lots of loss of life. So in the 1906 San Francisco, California earthquake was a 7.9. The 2012 Haiti earthquake was a 7.0. Nepal, but was really devastating because the conditions in Haiti were such to massively increase the damage and loss of life. Nepal in 2015 was a 7.8. Ecuador in 2016 was a 7.8. 8 to 9, there's maybe, and there's like a 15 a year. 7 to 8. From 8 to 9, that's a great earthquake. There's maybe 1 a year. These have severe economic impact and large loss of life. So Chile in 2010 was a magnitude 8.8. Mexico City in 1918, that was a magnitude 8.1. And greater than 9 are very rare. These are the largest recorded earthquakes, much less than 1 a year. They cause destruction over a vast area and massive loss of life is possible. So these are some of the biggest earthquakes ever. So Chile in 1960 was a 9.5. Alaska in 1964 was a 9.2. It's the biggest earthquake ever recorded in the US. Sumatra in 2004 was a 9.1, and Japan in 2011 was a 9.0. And that's famous for damaging the Fukushima nuclear power plant. I believe that is the one that damaged Fukushima. So the factors that determine structural damage are kind of complicated. So there is the intensity of the earthquake. Bigger the earthquake, the more damage you're likely to have. The duration of the vibrations, how long the earthquake lasts. The nature of the material on which the structure rests. So if you have loose soil or something, certain materials are likely to have much more severe issues in earthquakes than others. So like if you're on nice, solid, stable ground, your earthquake's not going to have much. If you're on looser, muddier ground, you could have very severe damage. And the design of the structure. Is the structure designed to handle earthquakes? Is it well anchored? How well is it anchored? Things like this. So destruction results from a variety of things. Things like the shaking of the ground, the amplification of waves based on the ground material. Certain materials are going to make the waves that occur much larger. And liquefaction of the ground, where saturated material, that's material that's full of water, turns fluid. And what can happen is underground objects may float to the surface, and objects may sink into the ground that has turned liquid when it wasn't liquid before. So here are some examples. These tilted buildings were rested on unconsolidated sediment that behaved like quicksand during the 1964 Niigata, Japan earthquake, and they basically fell over, which is both amusing and terrifying. And here's a video showing a number of examples of liquefaction, some of which are kind of hilarious, like having your car sink into the ground. Why is there no sound? This was the Christchurch earthquake in New Zealand. Two cars sinking into the dirt.
Just come in to check a couple of our family members, see if they're all right and got food and water.
Sinkholes can happen.
We're really quite stranded, really. Roads are bad, obviously.
Can you get my sister on TV?
We've just come from Brisbane where they've had the floods, and I'm not sure which is the worst. But
we're not really sure where we're going to go from here.
If it rock and rolls again tonight, well, we'll think about leaving.
Do what you always do in Canterbury, which is reach out to one another, be good neighbours, talk to one another, help each other out, do the very best you can. We will come through this.
Today, all New Zealanders breathe for you, Christchurch. Though your buildings are broken, your streets are watched, and your hearts are aching, your spirit will overcome.
So those are some examples of liquefaction. And much of the destruction results from things like landslides and ground subsidence, which can be very damaging. The biggest source of destruction in earthquakes is actually fires. Because earthquakes tend to damage the stuff we would use to fight fires. They break water mains, the distribution systems for water, but they can also make fires worse by breaking gas lines and things and releasing flammable gas to make fires worse. And then some of the worst damage from earthquakes, we get tsunamis. Tsunamis can be caused by undersea earthquakes. They can cause these massive waves that are extremely destructive. These are generated from big earthquakes on the ocean floor primarily. There is a tsunami warning system that uses ocean buoys to help warn people in the path of tsunamis, but that only works if you're sufficiently far away from the tsunami. So like the Indonesian tsunami the devastating Indonesian tsunami that happened relatively recently, the earthquake that caused it was just off the coast. So there was no time for warning. Also, most of the tsunami warning system is primarily in the Pacific. So, if there's an earthquake that's sending a big wave across the Pacific, it gets noticed. But if it happens close, it's hard to deal with. So here are some examples of damage caused by earthquakes. This is the Turrican Heights slide caused by the 1964 Alaska earthquakes, where this subdivision basically broke into blocks, and the blocks all slid on a layer of clay that was underneath the subdivision. and they just sort of rotated like 45 degrees. This was the most powerful earthquake ever recorded in the US, and it was up in Alaska. So this is a video about liquefaction and other forms of damage from earthquakes.
Hi there, Callan Bentley back once again for another Smart Figure. This time we're going to take a look at liquefaction, and after watching the video you should be able to describe what liquefaction is and why it's a hazard associated with earthquakes. Let's begin our discussion back in 1964 when there was a really big earthquake up in Alaska. This earthquake caused a lot of damage in many different places around the state. Here is some of the damage in downtown Anchorage. Look at the big difference in elevation between where the street was and where it ended up. Another example of that same phenomenon occurred in a little subdivision out on the outskirts of Anchorage called Turnagain Heights, and that was built on a series of sedimentary layers, including one which was a slippery layer called the Bootlegger Cove Clay. When shaking occurred, the land above the Bootlegger Cove Clay slipped on that clay, and it basically slid out into the sound. And so it broke into a series of these blocks, and they slid along this greasy base, and the houses that were built upon those blocks ended up being torn apart. So this is a photo which is actually vertical, so like the edges of the photo over here are actually vertical, and you can see that the trees are no longer vertical, and the house, of course, is just torn to pieces. Another aspect of seismic activity can be little sand volcanoes like the ones you see here. These form when you have a layer of loose material that's really saturated with water, and oftentimes it's capped with something that confines it, like well-packed soil in this diagram. When it's shaken, that sandy, watery material ends up flowing very easily out of little fractures in the surface. It ends up then producing these sand volcanoes with the material that's been displaced, but then the ground actually settles because the material has become more closely packed together. So after an earthquake, when you see these little sand volcanoes, realize that you're probably standing on a surface that is dropped by some amount. What would it be like if you had built a house on this area before this earthquake? What would happen to the house if it was built on a layer of material that basically turned into goop when it was shaken by seismic waves? If you guess that the house might tip over or sink into the ground, you'd be right. This is one of the major reasons that we really worry about liquefaction. It's not just a few sand volcanoes erupting in your lawn, it's basically undermining the foundation of your building. This is a building that tipped over in an earthquake in Mexico City due to liquefaction. Mexico City is the largest city in Mexico, and it's basically built on an ancient lake bed, which is really prone to this sort of behavior. So, on that happy note, let's conclude. Thanks again for your attention. This has been another Smart Figure.
Another thing that happened in that earthquake in 1964 in Alaska was that was mentioned in the figure. There was actually basically there's video out there of the bay basically draining and then get hit by a tsunami. There was a massive landslide, basically drained the bay, and then it's hit by a tsunami. It was fairly dramatic. So here is a short video about how tsunamis are generated by the displacement of the ocean floor during an earthquake. So you have a subducting plate, it builds up a bulge, storing energy, and then it releases, and that creates a tsunami, a wave that travels outwards. And while it's in the deep ocean, that wave is actually not very high, but moving quite quickly. And it slows down when it hits shallower water, and it piles up and gets much bigger. So here's a short video about tsunamis.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. In this video, we're going to take a look at tsunamis. After watching it, you should be able to describe why tsunamis occur and what areas of the world are at risk from tsunamis. So basically, anything that displaces seawater can cause a tsunami. It could be an asteroid impact, it could be a huge landslide, but the one that we want to focus on here in this chapter is the threat from earthquakes, and especially megathrust faults. So megathrust faults occur where we've got subducting oceanic crust, and when an earthquake occurs, it ends up displacing some of that crust, and that pushes seawater out of the way. Now, initially, out in the great depths of the ocean, where the water is very deep, 5.5 kilometers deep, these tsunamis move along very, very quickly, about the same speed that a jet aircraft flies at. But when the water gets shallower, there's more frictional drag on the waves, and they tend to slow down. And as they slow down, they tend to pile up. So when the water gets really shallow, say only 20 meters deep or so, they are moving much more slowly, but they end up piling up to much greater heights. If you're in a boat out at sea, you wouldn't even notice that a tsunami had moved underneath you because you'd only be displaced by a few centimeters. But if you're at the edge of the land where the sea gets very shallow, it ends up being a very big deal indeed. So these megathrust earthquakes that are generated along subduction zones ring the Pacific Ocean. We've got subduction happening on the coast of South America, up in Alaska, a little bit in Cascadia on the edge of the Pacific Northwest, Japan and the Indonesian islands, and even north of New Zealand and Tonga. All of those are ringing the Pacific Ocean, and smack dab in the middle of the Pacific Ocean is the U.S. state of Hawaii. So Hawaii really has a tremendous risk of tsunami because they could be generated in any direction. The good news is that there's plenty of time between when an earthquake occurs and when the tsunami hits Hawaii. And in this day and age, we have plenty of really nice examples where we have a big earthquake occurring, and then Hawaii gets plenty of warning, they evacuate the low-lying areas, and then the tsunami arrives without any major loss of life. However, over on the Indian Ocean, we had a real big wake-up call in 2004 when there was a really large earthquake there on the Sunda megathrust. This is the subduction of the Indian Australian plate underneath the Eurasian plate. That fault has ruptured several times. It ruptured in this section here in 2000 with a magnitude 7.9 quake. The really big one in 2004 was up here near Banda Aceh. And then there were also quakes in 2005, in 2007, and in 2010. But there's a big gap there in the middle, and that big gap is a seismic gap. That's one of the areas that we worry about for the future. And if you were in charge of predicting seismic risk in this area or tsunami risk, you might want to focus your attention on that seismic gap. All right, that's all I've got for you. Thanks very much for your attention. This has been another Smart Figure.
So when a submarine earthquake happens, some of that energy can be released in the water to form these huge waves called tsunamis. They can hit the shore and be very destructive. So here's another video about how earthquake, showing the process of earthquakes relating to tsunamis.
At DePaul University, we develop the whole student. Here you'll experience.
There are more tsunamis in the Pacific Ocean than any other. So in 2004, the world was taken by surprise when one of the largest recorded tsunamis of all time took place in the Indian Ocean. On December 26, 2004, Indonesia was rocked by the second largest recorded earthquake ever, 9.2 on the Richter scale. Minutes later, a 90-foot tsunami slammed into the Southeast Asian coastline. 225,000 men, women, and children lost their lives.
The Indonesian earthquake had as much energy in it as the total energy consumption in the United States in 1 year.
This enormous burst of energy had been released in just seconds. Once again, the world had been reminded of the Earth's awesome power. In the last 50 years, scientists were finally able to confirm a solid link between earthquakes and tsunamis. Although the Earth may seem to be a solid sphere, beneath the oceans and continents, it is divided into 8 major and many minor segments known as tectonic plates. Where they meet, they can grind and jostle against each other at fault lines, causing earthquakes. Geologists had long thought that the Cascadia fault line was incapable of generating a major quake. But Atwater's investigation has proved that it was highly active. The big worry for Atwater and the thousands of people who live in this region is that the Cascadia fault line bears an uncanny resemblance to another highly active fault line, the Sunda megathrust. It was an earthquake along this fault that was responsible for the Indian Ocean tsunami that killed nearly 250,000 people.
Where we get two tectonic plates coming together, such as in the case of the Indonesian tsunami in 2004, one plate pushes beneath the other plate and creates lots and lots of friction and tension and drags the upper plate down with it. And that process can take hundreds of years, even thousands of years. It's a very slow process. But eventually, the pressure of this one trying to push back up again wins, and it flips like that. And that creates a megathrust, a sudden movement of the seabed. And that's what creates a phenomenal tsunami.
So, where do most earthquakes occur? Most 95% of the energy from earthquakes occurs in a few narrow zones. All plate boundaries produce earthquakes, and some of the more common places are things like the Circum-Pacific Belt, around the Pacific, the Alpine Himalayan Belt, that also generates earthquakes. So all these boundaries produce earthquakes. So there's the Alpine Himalayan Belt here producing earthquakes. The Circum-Pacific Belt produces a lot of earthquakes. These are some of the more common places for earthquakes. And another place that has some but not as many are things like these along the mid-ocean ridge systems. There are earthquakes. So how do we deal with earthquakes? Well, one of the things we try and do is try and make some amount of predictions about earthquakes. There's two main types of ways we can try and forecast earthquakes. What would be most useful is short-term forecasts. Unfortunately, there is as of yet, no reliable method for short-range prediction. The general methods for trying to predict earthquakes look at precursor things like foreshocks or ground elevation changes. There are even some people who try and see if there's anything to that whole idea of animals reacting to earthquakes thing. There are actually some research groups that watch animals to see if they can see from their movements that an earthquake is going to come. But at the moment, there is no effective method for short-range forecasts. The best we can do is design systems that react very quickly to earthquakes and put themselves into a safe state. So, like Japan, which gets a lot of earthquakes, has developed things like utility systems that turn themselves off when earthquakes or shaking is detected. So, because one of the big problems with earthquakes is things like water lines and gas lines and things break and make the situation worse. So they're designed to cut off the gas and the water lines, turn them off so that if they break, they don't do any additional damage. There's just a leak later, but it's like a small leak that you can deal with. Long-range forecasts, we have a bit better luck with, but these are all probabilistics. So we can do things like study paleoseismology. We can study past earthquakes to try and understand how earthquakes have happened in the past and what has occurred and whether this location is likely to have evidence of, likely to have earthquakes again. And seismic gaps. The premise is that earthquakes are generally repetitive because they're powered by the grinding of continental plates against each other. And a region has a given probability of a quake, and you can sort of talk about a place being overdue. So you expect a quake every 100 years, and it's been 120, you expect a quake every 20 years and it's been 30 years since the last earthquake, you're probably likely to have an earthquake soon because you've probably built up a lot of tension and it hasn't gotten released yet. Or like was in that previous smart figure where they were showing how those earthquakes along the Sunda megathrust, there was that bit in the middle that hadn't had an earthquake. So it probably still had all that built up tension that needed to be released. So it's likely to have another earthquake at some point. So that's how you can study seismic gaps. So paleoseismology is the study of prehistoric earthquakes, because when an earthquake happens, the ground moves, and then you get new sediment and erosion on top of that movement, and that gets recorded. So sort of the pattern of the earthquakes, you can find evidence of past earthquakes by looking at the geology of the earth. So here is sort of what you start with the fault. First earthquake, one side moves up, the other moves down. It erodes down a bit and evens off. Then it gets displaced in the second earthquake. You get another set of erosion and evening off. And then a third earthquake, and again another set of erosion and evening off. And when you look at the sediment, you've got this sort of pattern of sediment from various earthquakes recorded into the earth. Now, to minimize earthquake hazards, the biggest factor is really how your buildings are constructed and what they're constructed on. Earthquakes don't kill people, buildings kill people. So, if you're in an earthquake in the middle of a field, you're probably fine, even if it's an extremely severe earthquake. You might get tossed around a bit if it's extremely severe, but you're unlikely to have anything immediately happen to you. However, if you're in a building, the building might collapse on you, and that's bad. So one of the things you can do is build earthquake-resistant structures. So in places that have had lots of earthquakes, they have, there's very detailed codes dictating how you have to build buildings so that they're resistant to earthquakes, so that they'll hold up. And also, you see things in the design of historic buildings in places that have had lots of earthquakes. They often have more buildings that are designed in such a way that they're easy to repair. They'll bend and jiggle, but they're not likely to fall down. So you might get some damage to your walls, but your walls are easy to fix. So if you look at like traditional Japanese or Korean buildings, a lot of them are sort of slightly decoupled from the ground and things like that. Those are much easier, those handle, and they're designed in a way that they're a little more flexible. Those handle earthquakes better. So earthquake warning systems measuring P waves shut down infrastructure in Japan immediately. This keeps that infrastructure from causing more damage. So one of the things that's really useful about earthquakes, however, is that we've discovered a lot about the interior of the earth from the waves generated by earthquakes. So most of our knowledge of the Earth's interior comes from the study of P and S earthquake waves, because these waves will travel through the Earth and allow us to get an understanding of what's going on inside here, because they're affected by what they pass through. So the travel times of P and S waves traveling through the Earth can vary depending on the properties of the materials, and S waves will only travel through solids. And if you've ever had an ultrasound for various medical purposes, an ultrasound is doing something similar to what we do with earthquakes and the Earth. They're, P waves are basically sound waves. They send waves traveling through the structure, and how they reflect and refract and bend allows us to figure out what the internal structure is. An ultrasound does that with your internal organs. It sends wave in, high frequency sound waves into your body, they bounce off of your internal organs, and you can image the inside of your body. By earthquakes occurring, send seismic waves through the interior of the earth, and how they get bent and distorted and reflect, etc., lets us get an idea of the internal structure of the earth. So the velocity of body waves is dependent on the density of the interior of the earth. And as the earth's interior generally increases in density with depth, when you move from something that has, when waves travel from something where they have one speed to another speed, they bend and refract. So as the earth's interior generally increases in density with depth, body waves will curve and refract. And geophysicists can use the travel velocity, the refraction pattern, and the travel path to interpret our modern view of the Earth's structure. We have a pretty good actual understanding of what's inside, including some things we're not going to show in this. So we're going to show an idealized model of the Earth's structure where it's made of a series of balls. But in actuality, there's like weird, big, lumpy things, and it's much more chaotic. So here are some of the possible paths that earthquake waves can take. They will have curved paths. They can be diffracted along the surface of the liquid outer core. They bend when they pass into and reflect. They can reflect off that surface. They could reflect off the surface, and you have refracted waves through here. And some of this is also, P waves can go through the liquid outer core, but S waves cannot. So S waves will be blocked, and they'll have a shadow where you don't see S waves. And this is sort of an idealized structure. These are not perfect spheres. They're not perfectly round. There's weird lumps and strange bulges and such inside. But this is our general idea. So if you have a seismic wave traveling through the Earth's interior, S waves stop at the liquid outer core. And so there's a big shadow zone where you get no direct arrival of S waves. But P waves can pass through. There is a small zone where you get a shadow from the refraction because they bend as they enter the liquid, the more dense core. Much like if you have a light sphere and you have light shining through it, there will actually be a ring of shadow where no light comes out. S waves do not travel through the liquid outer core, while the P waves get refracted, bent at the density boundaries. So here is a short summary of the internal structure of the Earth.
If we could split open our planet, we would see that it is made up of various zones. The Earth is approximately 8,000 miles or 13,000 kilometers in diameter, from the North Pole to the South Pole. At the center, we have what we call the inner core. It is thought to be a solid metal ball, about 750 miles or 1,200 kilometers thick. This center core is under extreme pressure and is believed to be at least 5,000 degrees Fahrenheit or 2,760 degrees Celsius. Surrounding the inner core is the outer core. This area is about 1,400 miles or 2,300 kilometers thick and is believed to be molten or liquid rock. Nickel and iron are probably the main elements of the outer core. Next is the mantle, approximately 1,800 miles or 2,900 kilometers thick. Geologists think that most of the mantle is solid rock. However, towards the top of this layer, there exists an area of hot, thick, molten rock. This area is called the asthenosphere. And above this area is the cool and rigid outer shell of the Earth, which we call the crust. Geologists sometimes refer to the crust and the solid area directly below it as the lithosphere. As we take a closer look at our diagram, we see that on dry land, the crust is a mere 20 to 60 miles or 30 to 100 kilometers thick. The rock that is similar to the common rock, granite, makes up most of this section of the crust. And under the ocean, the crust is a much thinner layer of rocky material similar to basalt. This section of the crust is approximately 3 to 6 miles, or 5 to 10 kilometers thick.
So if we look at the properties of the Earth and we look at the layers based on these properties, the outermost layer is this thin, rocky outer layer, the crust that varies in thickness. It's about 7 kilometers or 5 miles thick in oceanic regions. And the continental crust averages about 35 to 40 kilometers or 20 to 25 miles thick. And so we've never actually drilled a hole through the crust. So neither of the deepest attempts have made it through the crust. The deepest one was 12 kilometers deep, but it was in continental crust. So it didn't make it through. And I think the other one was a good deal less, but it was in oceanic crust. So it may have actually made it closer to the mantle. But it was also underwater, which made the whole process more complicated. So this exceeds more than 70 kilometers or 40 miles thick in some mountainous region, the continental crust. The continental crust is the upper crust composed of granitic rocks. The lower crust is more akin to basalt. The average density is about 2.7 grams per cubic centimeter, and it's up to about 4 billion years old. Oceanic crust is basaltic in composition. Its density is about 3 grams per cubic centimeter, and it's pretty young. It's on the order of 180 million years or less, much younger than the continental crust. The mantle below the crust, to about a depth of 2,900 kilometers or 1,800 miles, is the mantle. The composition of the uppermost mantle is the igneous rock peridotite, and it changes at greater depths. We have the best idea of the upper mantle because sometimes the upper mantle will basically come out of volcanoes. Then above that, below that, we have the outer core, which is liquid. We know this because S waves don't pass through it. And this is roughly a sphere with a radius of 3,486 kilometers or 2,161 miles. And it's composed of an iron nickel alloy. And it has an average density of nearly 11 grams per cubic centimeter. And the inner core is a sphere with a radius of 1,216 kilometers, or about 754 miles. And it behaves like a solid due to extreme pressure. And its density is about 13 grams per cubic centimeter. So we have the inner core, which is solid iron and nickel. The outer core, which is liquid iron and nickel, which is where our magnetic field is generated. Then we have the mantle. The lower mantle is hot but strong because of high pressure. The upper mantle is softer, where we have the hot, weak layer of the asthenosphere, and then the top layer of the uppermost mantle, and the crust is the lithosphere. So temperature and pressure increase as you go down with depth. So that was chapter 5. We still have a decent amount of time, so I'll get a little bit into chapter 6. So chapter 5 is the limit to what will be on the next test. We're still a bit ahead. And so that's what we're going to cover there. And additionally, I think that's just a reminder that that is the point to where next test and next set of homeworks and stuff is. So chapter 6, we're going to talk about volcanoes and other igneous activity. Things that happen with molten rock, basically. So we'll look at a couple different, we'll compare and contrast eruptions of a couple different volcanoes. The 1980 eruption of Mount St. Helens with the most recent eruption of Kilauea, which began in 1983. That's technically slightly incorrect. Since this came out, Kilauea had a short pause in erupting and then started up again. So I think the most recent eruption of Kilauea started in like 2021 or something. But it did erupt for, since 1980, you know, the longest eruption that had ever been recorded in modern history was Kilauea, just continuously erupting since from 1983 on until, but when did it stop? I haven't looked up. Yeah, it stopped for like less than a year. So we're up to this. Let's see. Yeah, 1983 to 2018, then it started up again 2020 to 2021, 2021 to 2023, and then it's sort of been going on since 2024. So it paused a couple times, but it's been more or less erupting continuously since 1983. We'll explain why some volcanic eruptions are explosive and others are more quiescent. We'll list and describe the 3 categories of materials extruded during a volcanic eruption. We'll draw and label a diagram that illustrates the basic features of a typical volcanic cone. We'll summarize the characteristics of shield volcanoes and provide one example of this type of volcano. We'll describe the formation, size, and composition of cinder cones. We'll list the characteristics of composite volcanoes and describe how they form. We'll go over the major geologic hazards associated with volcanoes. We'll list volcanic landforms other than shield, cinder, and composite volcanoes and describe their formation. We'll compare and contrast these intrusive igneous structures: dikes, sills, batholiths, stocks, and laccoliths. We'll summarize the major processes that generate magma from solid rock. We'll explain how the global distribution of volcanic activity is related to plate tectonics. So, let's start by comparing 2 volcanic eruptions, Mount St. Helens and Kilauea. Mount St. Helens in Washington in 1980 had the largest historic eruption in North America. That means, you know, during recorded history. There's definitely bigger ones in the past, but we don't have like actual historical records of them. This one was caught on camera by more or less pure luck. It erupted a cubic kilometer of ash and rock debris. It had associated ash, pyroclastic flows, and mud flows, and claimed a total of 59 lives. It basically blew the top off of the mountain. Well, actually, the side off of the mountain, but also a bit of the top, most of the top. So Kilauea, Hawaii, began in 1983, the most recent of at least 50 eruptive phases. Been more, there was a pause and then it started up again. It's been non-explosive eruptions of fluid lavas. It's destroyed 182 homes and a national park visitor center. I'm not sure if it's actually claimed any lives, though. Because the thing about Kilauea is that it releases a lot of lava. But the lava doesn't move that fast. So as a person, you can get the heck out of the way. Your house does not have the ability to get the heck out of the way. But yeah, so this has a lake of lava. that you can see in things like that. So this is Mount St. Helens. These are before and after photographs of Mount St. Helens. You can see how this is before, this is after. See how there was lots of trees and a nice blue lake. And now there are no trees and a lake covered in trees. And the mountain's now 1,350 feet shorter. It lost 1,000 feet of height. The whole side just blew up. So it blew out the entire north flank, which just sort of plunked out and slid down, leaving a gaping hole. And in a brief moment, the prominent volcano was lowered by about 1,350 feet. And it was caught on camera. While Kilauea just dumps out lava at a steady rate. So magma is the source material for volcanic eruptions. Now that magma can have different compositions. If it's basaltic or mafic and rich in dark silicates, that tends to come from the partial melting of the upper mantle. That's deep magma. While granitic or felsic magma that's rich in light silicates generally results from the melting of continental crust. That's shallower magma usually. Basaltic magma is hotter, granitic magma is cooler, and basaltic magma is less viscous. Granitic magma is more viscous. So basaltic magma flows more easily, it flows out relatively easily. It doesn't get stuck as easily. Granitic magma is thicker and gooier. It also has more volatiles in it, more dissolved water and gas that can build up pressure. So basaltic magma tends to be associated with more peaceful eruptions. Granitic magma tends to be associated with more violent eruptions. So basaltic magma has the lowest silica content, the lowest gas content, the highest eruptive temperature, the least viscosity, the least tendency to form pyroclastics, and is associated with things like shield volcanoes, basaltic plateaus, and some cinder cones. Andesitic lava is intermediate. It has intermediate silica content, intermediate gas content. It has an intermediate temperature. It has intermediate viscosity and an intermediate tendency to form pyroclastics. It's associated with composite cones. These are the tallest and steepest volcanoes because they'll alternate between generating lots of ash and particles, which can build up steep walls, a steep mountainside, and magma, which will basically glue it in place, and lava, which will basically glue that into place, allowing it to build the tallest and steepest of volcanoes. So that classic volcano shape that's, you know, very conical in the middle of nowhere, standing up with a caldera on top, that's a composite volcano. So like Mount Fuji, well, Mount St. Helens in the previous image was also a composite. And then rhyolitic or granitic or felsic magma has the most silica content, the most gas content. It's at the lowest temperature. It has the greatest viscosity, the greatest tendency to form pyroclastics. It's associated with pyroclastic flow deposits and lava domes. Now, whether an eruption is effusive, flowing easily, flooding outwards, and being liquidy, or explosive, depends on a couple of factors. It's controlled primarily by the viscosity, the resistance to flow. A higher silica content leads to a higher viscosity. Higher viscosities are more explosive. You can think of it as that higher viscosities tend to clog the pipes. And if the pipe gets clogged and pressure builds up, stuff is more likely to explode than just flow outwards. And gas content is a measure of how much dissolved gases are present in the magma. Higher viscosity of more trapped gases. These more trapped gases help increase the pressure, which makes the volcanic eruption more explosive. So here's an eruption column generated by viscous silica-rich magma. Lots of pyroclastics, little bits of rock and material flying out. These can be, it's blowing up way into the air. This can settle down and create these devastating pyroclastic flows that can be very destructive. This is what, the ash from an eruption like this is what buried Pompeii. So here is a short video about this sort of eruption. This is an image of one at Metro Island. So the start to the volcano you can see here is that massive column of ash and dust and pyroclastics. Here's a pyroclastic flow rolling down the side of the volcano. That's like superheated ash and toxic gas all rolling along varying places. Now, the viscosity of magma is dependent on two main factors: its temperature and its silica content. The hotter it is, the more easily it flows. Much like if you take honey and you warm it up, it'll flow more easily. That's generally true. And in general, magmas that originate deep within the earth have higher temperatures. And then the more silica is in it, the thicker and gooier it'll be. The higher the silica content, the higher the viscosity. So in general, magmas that generate at shallow depths have a higher silica content. Peaceful eruptions generally involve basaltic magmas. These originate deep within the earth and therefore are very hot. They also have a relatively low silica content. And due to the combination of high temperature and low silica content, basaltic magma flows easily, resulting in peaceful eruptions. The least viscous magma we currently see erupting on Earth is Hawaiian magma. The Hawaiian lava. It's the most flowing lava we currently see. We have evidence of even less viscous lava happening in the past from things like flood basalts, but the currently lava you can actually go out and see, that's in Hawaii. Most basaltic eruptions happen in two distinct settings along the length of a divergent plate boundary, like in Iceland. So in isolated areas where a lithospheric plate moves over an unusually hot and stationary zone in the upper mantle called the hot spot or a mantle plume. So if you want to see basaltic magma coming from a divergent plate boundary, you go to Iceland. If you want to see basaltic magma coming from a hot spot, that's Hawaii. So the Hawaiian Islands and the Emperor Seamounts are a continuous series of volcanoes formed over the past 70 million years by the hot spot that is currently under the big island of Hawaii. So you have a hot spot making islands, and then you have older, but as you get progressively older as you travel along the chain, and there's a set of underwater volcanoes that are even older. And these are formed as the Pacific Plate moves over the hot spot. So here is a short video about how Hawaii formed.
Build a website you love with Wix. For your words,
Hawaii sits in the middle of the Pacific Ocean and nowhere near the edge of a tectonic plate where volcanoes are usually found. So how did the island chain form with all of its volcanoes? The island chain is located over a hot spot fueled by a mantle plume of heated rock. Solid rock at the bottom of the Earth's mantle is heated by the planet's core. That hot rock slowly rises and pushes up the crust, forming a bulge. Under that bulge, some of the rock melts into magma. Magma makes its way to the surface through cracks in the crust. Once it's above ground, it's known as lava. Hawaiian volcanoes produce lava flows made of melted basalt, which is more liquid than lava produced by more explosive volcanoes like Mount St. Helens. Basaltic lava flows form volcanoes with gently sloping sides. A lake of liquid lava can sometimes be seen at the top of active volcanoes like Kilauea. Sometimes the magma can flow underground to the sides of the main vent and erupt out of cracks in the ground called fissures. When lava meets ocean, the island grows, but you may not want to get too close. That steam is hydrochloric acid laced with tiny shards of volcanic glass. The Pacific Plate is moving to the northwest, dragging the crust over the hotspot and creating islands as it goes. The hotspot itself might be moving too. The volcanoes on Niihau and Kauai, the northwesternmost islands in the chain, are about 5 million years old. The Big Island of Hawaii is the youngest and started forming about 400,000 years ago. It's still changing and is home to 4 active volcanoes. Eventually, the Big Island will no longer be over the hotspot, and a new island will grow next to it. But maps won't need updating for a while. Loihi won't break the ocean surface for another 200,000 years, give or take. For Scientific American, I'm Kelsey Kennedy.
Now, explosive eruptions generally occur along subduction zones and involve silica-rich magma. And magma that originates within the subduction zone are not deep and are therefore cooler in temperature, and they're also higher in silica content. And due to the combination of a low temperature and a high silica content, these magmas are very viscous, and this causes explosive eruptions. So here are 6 different types of volcanic eruptions. But here's an image of Mount St. Helens erupting in 1980, because it was actually caught on camera. And we're going to stop there. So we'll get back to this next week. Continue talking about volcanoes. I need to go through these slides and fix all the YouTube videos. I thought they were okay, but apparently there was an issue with